Now let's look at one more situation where we're trying to optimize something to do with a physical object of some kind, volumes and surface areas and so forth. This is a box with a square base and open top, must have a volume of 32,000 cubic centimeters. So that's a requirement on the volume. Find the dimensions of the box that minimizes the amount of material used. So this kind of goes back to what we were doing with the circular or the cylindrical can in the last example, but with a different shape. So let's illustrate the situation here. We have a box, but it's got an open top to it. So we have to kind of, oops, that didn't work so well. Give me just a second here. Okay, maybe that'll kind of work out okay for our purposes. So kind of a little lopsided, but it'll do. So it has height to it, we'll just call that h, and then it's square, so the dimensions of the sides of the top and the bottom are the same. So we'll call b the length of the sides along the base. And so the volume is length times width times height, but in this case length and width are identical, so those are both b. b and h would tell us that we have b squared h. So that's volume. Now surface area is going to be made up of b squared, which is the base. Remember, we don't have a top on it, so we only just have the base to worry about, plus the surface area of the four sides. Each side has a surface area of BH, and there's four sides, so 4BH would be the surface area of the four sides. So that together added up is the full surface area of the box. Now which one are we trying to optimize here is the question. In this case we're trying to optimize the surface area. Okay, so what we're going to do here is we need to use the first derivative on the surface area, but we need to do something with both variables. We need to substitute in for either b or h. What I'm going to do is go over here to this v, which we know the volume needs to be 32,000, so that has a number for it. We're going to solve this one for h. So I'm going to divide both sides by b squared, and we'll have h is equal to 32,000 over b squared. Okay, so now I can substitute this in over here. S is equal to b squared plus 4b times 32,000 over b squared. And we'll notice that the b will go ahead and reduce down here. So I have b squared plus 128,000, that's the 4 multiplied by the 32,000, over b. So this is what we're going to need to optimize. So keep in mind that we're about to find the derivative of this. So why don't we go ahead and make that b to the negative first power. So s prime is going to be 2b minus 128,000 b to the negative 2. And so we'll just put that back down in the denominator. Okay, something like this. So now we'll set that equal to 0 so we can solve for the critical value here. First derivative set that equal to 0. Much like the last example, I'm going to multiply both sides by b squared. And that will distribute to both of these terms here, but get rid of the denominator. So 0 equals 2b cubed minus 128,000. Okay, so let's see, we got to solve for b cubed. So when I do the move over the 128,000, divide by 2, b cubed is actually 64,000. And that way we can take the cube root, and the number works really good here. It's equal to exactly 40. So unlike the last example, I'm just going to go ahead and assume that this is going to be referring to the location where the minimum will occur for surface area. And so the dimensions of this particular box, we need to have the base at 40 centimeters, and then for the height, our formula for that was 32,000 over b squared, so 32,000 over 40 squared, and that's going to equal to 20 centimeters. So the dimensions here would be 40 centimeters height, or should I say length, 40 centimeters width, and 20 centimeters height.